I believe we can proceed uh, now, uh, and we can let people join as in uh, the time proceeds. Hello, everyone. Hi, thanks for joining on a on a Sunday morning. Hi, Arjun, Pranay, Sumit, Tejas. Great to see all of you here. Um, I would just before proceeding, I would give you a brief introduction of Horizons Achievers Program. Horizons Achievers Program are for curious and ambitious high school students. These are live interactive micro courses which would be conducted over summer 2025. We are offering a very variety of courses across disciplines this time. Why we are joining today is for learning circles. Learning circles essentially is it too loud in my background? There are a couple of noises, I believe. Can you hear the noises or should I change it? Okay, yeah. Thanks for letting me know. Yeah, there's just something going on in the background. Yeah. So why we are essentially meeting is for the learning circles. The objective of the learning circles is we would be doing a live hands-on workshop wherein we would be giving some certain challenges for you to engage, certain activities across the three different courses that we are going to offer in this summer 2025. Moving on, we have been joined today by Gautam, who is teaching fellow for applied data science for MI and AI. Shantripta Sharma, who is going to be the teaching fellow for the mathematical foundations of computer science. Unfortunately, Akash, who would be the teaching fellow for AI for tomorrow's world, hasn't been able to join us due to some medical emergency. But essentially, all of us would be going through, how AI helps what are the features, what are the applications of AI. So we would not be only we would be talking about different applications, how to analyze real world data, uncovering the math behind all the intelligent systems with both of them. Uh, Proceeding further, I would request Gautam and Santripta to begin with the activity which they have created for all of you.
Sure. So, hi guys. As mentioned, I'm Santrip. I am a fourth year CS major here at Ashoka, and I'm very excited to kind of just deliver the session for you guys and just dive into. So, what we're going to do, if you could just go to the next slide, there's not much there, but nonetheless, what we're going to be doing is we're going to be looking at one of these primitives for a lot of machine learning and artificial intelligence as it exists today, which is this thing called linear regression, right? We're just kind of going to be diving into like the fundamentals of it, what it's all about, and why we care about it. And what I'd like is if we could keep, like, it's a pretty small session, so I'd like if we could kind of keep it a bit interactive. So we might kind of ask you guys about what your experiences or what your thoughts are on what we're covering. And if you guys could just type in chat or just unmute your mics and speak, that'd be great, right? So just to begin, I think the first thing I'll ask is, have any of you heard of the concept of linear regression at all? So we kind of know what we're working with in terms of experience. So just go for it. No.
No,
Yeah.
I haven't heard of it before.
Okay, lovely. What about the rest? No.
I haven't either.
All right. And what about Sumit? And the rest? Okay, so the general sense I get is this is something that's new for all of you, which is a great thing because then it's a good learning outcome for all of you to kind of come out of the session and have an idea of this thing. And again, uh, I like to once again say it's one of the most kind of primitive or one of the most kind of basic ideas in all of ML. And this simple idea is the same thing that gets extended over, to a much higher scale in even the most complex kind of artificial intelligence systems like ChatGPT or Claude, if you guys are familiar, that we see today, right? So you take the same basic idea and just apply it in a much larger scale, right? And you kind of start building up those larger networks, right? So I mean, what we're gonna do, I think, is we're gonna share this whiteboard, and you guys will just have to let me know if you can see. Oh, sorry, I think that stops the screen share, so try to restart that later. But do you guys, are you guys able to kind of,
Yeah, we can see the I can see the whiteboard.
you can see the whiteboard? Okay, lovely then. So yes, so what we're gonna be covering, and pardon my handwriting here, is this thing called linear regression. Oh God, that's really awful. But I hope, yeah, there you go. That's text. Oh, that's much better. Right. So what the idea here is, let me see if I can just, yeah. So what the basic idea here is in machine learning, right? What we're typically dealing with is some sort of data, right? You're given some sort of data, and we'll pick up an example and we try to understand what data looks like first. So imagine you're given a task, right? So machine learning is all about prediction. So I give you some values about a certain object, and you're expected to predict some property of that object, right? That is dependent upon those values. So what ends up happening is, for instance, a common kind of problem you might deal with is if I give you, let's say I give you the square footage. I don't know if I can write the square footage, number of bedrooms, number of floors. So if I give you these three properties for a house, right, you would agree that this kind of defines a house in some sense, right? So if I give you these three properties of a house, like a machine learning problem might be to take these three properties and somehow predict the price of the house, right? So that is kind of a classical machine learning problem, right? So there's some object, so in this case, a house in the real world, you're given some properties about it, and you have this data for a bunch of houses. So you have square footage, number of bedrooms, number of floors for a bunch of houses, right? And from that, what you want to do is you want to learn some kind of relationship between these three variables, these technically this price of the house and these three variables. So you want to kind of take the price of the house and also take these three variables. So like if you give me a new house now, right? So if you give me a new house with a square footage of 3,000 square feet, three bedrooms and two floors, then I should be able to tell you a good guess or a good prediction, right? For the price of that house. And this is essentially what linear regression tries to do. This is like linear regression is one way of modeling this relationship, right? So are you guys familiar with? I know everyone's coming from a bunch of backgrounds here, so I'll try to keep it towards open-ended. But are you guys familiar with like the equation of a line?
Like
Can someone spell it out for me?
linear line, like y equals mx plus c.
Perfect, right? So what would you call M and what would you call C here?
Well, usually m is the gradient and c is the y-intercept.
Sure. So yeah, perfect. So gradient or slope or whatever you call it, basically it's saying that how quickly does as x changes by one, how much will y change, right? And like you said, C is the intercept. It's where when x is zero, what is the y value, right? So where do you intersect the y-axis line, right? So perfect. So see what our data kind of looks like right now, the way we've explained it is, let's say you have a house with 3,000 square feet, four bedrooms and one floor. You can kind of represent it in this form as like a what we call a three tuple. So this is a three tuple, right? Or if you guys are familiar with vectors, this is a vector of three dimensions, right? Or for now, like for all intents and purposes, you can kind of just think of it as a list of numbers, right? So does everyone agree, or does it make sense to everyone how this kind of in under this scheme, how this kind of represents a house, right?
Yeah, it makes sense. Just
Yes.
considering all the factors that affect it.
Yeah. So maybe this is 2,500, two bedrooms, two floors. That's a strange house, but um, you can kind of see how you could end up with like maybe 30 or 50 or such houses looking like this. And from that, you to deduce some kind of relationship between um these kind of essentially two quantities, right? Or one set of quantities and the price of the house, right? So what linear regression does is it's going to model this. So just for some terminology, each of these things on the left here, the square footage, number of bedrooms, and number of floors, they're called features, right? Feature variables. So like when you go to buy something, like when you go to buy, say, a laptop, or when you go to buy a phone, you might look at this is um the camera quality, right? This is how many megapixels it has. That's a feature. This is what the RAM size is, right? This is what the processor speed is. So those are all features of the phone. So in the same way, these are all features of our house. So you call these things feature variables. And the thing on the right is either called the predictor or the label, right? Because this is something we want to predict based on the features, or this is something that we want to label the house with based on the features of the house. So what linear regression does is, remember, what we're trying to do again is model a relationship between these features and this predictor, right? So again, by the way, if I'm going too fast, if you guys are not tracking with anything, just feel free to put something in the chat, raise your hand and speak, or not even raise your hand, just speak, right? But what a linear regression, the reason it's called linear regression is it tries to model this relationship as a linear function, so as a line in some sense, right? So let's say you only had one feature, right? So let's say your feature was just square footage and your predictor was just price of the house. What you would do is you would kind of model your system, or model your kind of relationship as y being the predictor, so y being the price of the house, and x being the square footage of the house, right? So what that means is you would want your system to you expect. So this is a hypothesis you're putting, that I expect my prices to be a linear function, or a y equal to mx plus c form of my feature vectors or my feature variables, right? So what that means is, in this case, we would want something like 3000 is equal to, so I'm just taking again, sorry, not 3000 is equal to. So I'm just taking again, I'm just taking the square footage as the feature right now. But what that gives you is this kind of setup where, let's say, this house cost, like we know that this house cost us, I don't know, some currency. I'm gonna draw some currency might cost 25,000, and the other house in some currency costs, I don't know, 15,000, right? So let's say those are that's the data we have. I don't know why it's going into a new line, but so the basic kind of setup we want is, we want our equation to look like 25,000 is equal to uh, m into 3000 plus c, right? But at the same time, we also want it to kind of look like um, this. So 15,000 is equal to m into 2500 plus c. Does this problem formulation make sense to you guys?
Yeah, it makes sense. You're
Right.
just fine. You're just sort of using the predictor. And since you're doing that, you can get two equations and find C.
So, correct. So basically, remember, one important thing to note here is we are putting a hypothesis out here. We're making a claim that this is what a relationship looks like. It may not actually be the case in the real world, but we're making a claim that this is what it looks like. And the idea is that once you have a bunch of such equations, so once you have a bunch of such collected data points, you have looked at 100 houses, right? So I have 100 equations in two variables. The problem is, when you have more equations and variables, sometimes you might not have an exact solution, right? Like there might not be a pair of M and C which works for both of these um, equations. I mean, this case mein hoga, but once you kind of expand this, you might find that you find a line for 2 points, but the third point doesn't lie on that line, right? So that is the purpose of machine learning, right? Like we made a hypothesis about our data looking mostly linear, but in reality, there's a bit of noise to house prices, right? There's also contributions from other variables we aren't really capturing here. So the number of bedrooms, the number of floors, also the number of, or sorry, let's say the distance from the airport is also a factor that probably affects it. We aren't kind of including it in our model right now. And because of that, it's a partial model and it won't be complete, right? So what that means is, this equation, like if it had a perfect solution, you could just solve for MNC and you're done. You've kind of found a line that maps this relation. And once you found MNC, what you can do is, if I give you a new point, and this is the whole motivation of linear regression, this is why we care about doing it. If I give you a new set of house values, right? So if I give you, I have a new house which I don't know the price for. I'm trying to set a price for that house. I give you a house which has 4,500 square feet, 4 rooms, three floors, right? Now, once you have MNC, you can just plug, that square footage and all those variables into the equation and figure out what a price should be based on this model, right? So it's a prediction for that price of the house. So that's why we care about this. And that's why we have to devise some mechanism for kind of coming up with an MNC that work somewhat well, right? So now that's enough talking. I think you guys might be also getting tired of that. So now let's try to draw a figure for this. So I guess Gautam, if you wanna just have a go at that. So what the basic hmm.
Uh, can you hear me? Yeah. Uh, so what I'll do is I'll try to show it visually what Santripta was showing you earlier. So let me just quickly make a figure. So suppose we have a graph here, and on the x-axis, you can take the area, and on the y-axis, you can take the prices. So what Sandripta was saying earlier, how when you have to find only two things here, M and C, but you have hundreds of equation or hundreds of entries, so it will usually look something like you have points here. Can you see the point? Yeah. So, oops. Second. Santripta, could you draw a few points as well? Yeah. So you have a few points here, a few points here. So these are all some square foot area and their associated prices. So ideally, when you are only solving for two equation, you'd find a perfect solution where you get a value of M and C such that the line passes through both the points. But now you have hundred of points and you can't find a perfect solution such that the line will pass through every point. So what it's trying to say is what we usually do or what a linear regression model usually do is when we take all this data, we try to find a point or we try to find a solution or a line such that it passes through these points. Let me just make it red. And then this line will have a solution of M and C such that when you put in any future value, of a area of a square foot area of a new house, it will give you some predicted answer, some approximate answer, which will not be correct, but will lie within some error range or some range of your expected area. And now the next question essentially becomes is how do you find such a line? Just, just give me 1 second. I'll draw this. Yeah. So, so the next question essentially becomes is how do you find such a line? Because if you try to solve it just by computing, uh, just by taking these equation and try to find MNC, you'll find multiple values. So the one way that you can find is through some notion of a distance between the line and the points. Santripta, do you want to give some intuition behind that?
Yeah, so I think first let's maybe have it kind of as an open and maybe question. So
Oh
just
yeah.
guys, do you have any so basically, what we're trying to find right now is some kind of intuitive idea for what a well-fit line would be, right? So what we're doing is we have some data which looks like this. So again, you understand how the data is created, right? So the points, how we're kind of plotting them. Does that make sense to everyone?
Yeah, that makes sense. It's
Good.
basically
Mhm.
it's like the line of best fit that we usually do.
Exactly. It is precisely like the line of best fit idea precisely comes from linear regression, right? But now the question is, how do you even quantify something like fit, right? Like, what is a well fit line? Like, okay, like if I was to draw this line, or if I was to draw this line, why is the red line better fit than, all of these lines? Like, why is this line not I mean, this data is not very directional in some sense. Okay. So what pass, yeah, sorry, Pranay, you were saying something.
Yeah, No, I thought it was a question that you were asking
It
us.
is a question. I
Okay,
just
It is a question.
I
sorry.
think the line of best fit it's based on the distance of the points both below and above the line being like closer to the line.
Sure.
So that the
So
closer all the points are to the line, both
reason.
above and below, will define whether it's
Yeah.
got a good
I
fit.
think, yeah, so that's one notion. So we'll come back to that. And I think
Mhm.
Arjun is also talking about you look for the line which passes through the most points,
Most
right?
points.
So I'll tell you something. The reason you do actually care about this in some systems. So in some systems where you know that your system is supposed to be deterministic, it's supposed to not have any error. You actually do this. So in a lot of computer vision applications, this is actually a valid kind of approach, right? If in case you guys want extra reading, but this is high level reading, so don't worry about it. It's called SIFT, SIF, not SIFT, sorry. It's called RANSAC, so random sample consensus. But again, that's just a kind of side throwaway thing. Don't worry about that. But that is a kind of approach we do use in those kinds of problems where the system is supposed to be deterministic. That is, there's not supposed to be any error. But because in the machine learning problem, inherently, by the fact that our data is noisy, right, by the fact that we're not representing all the variables, we do expect there to be some, like we do expect the data to not perfectly conform to our variables. So sometimes the line of best fit, so I'll give you an example, in fact. Sometimes your line of best fit, and I'm drawing a rough graph here, sorry, Gautam, I know you like your straight lines, but so if this is my point, imagine my points basically lie along two lines, right? Like so, let's say like this is my data. So your method would kind of give us this as the line of best fit, right? Which again makes sense for certain kind of problems. But here, potentially the better line of best fit you would care about is this one, right? So Arjun, does that make sense? Why, like your solution, while it makes sense in some cases, here we possibly want to look for a different idea, right? Cool. So now let's get back to the distance idea that, oh my God, what is, why is he? Oh my God. Yeah, that's the, can I draw? Oh, I can draw over it. Beautiful. So yeah, this is what your
Yeah.
data might look like, right? So there's no exact one line that, like you could think of many lines that pass through many points, right? So it's not always the most easy thing to even compute,
Hmm.
right? So what we do kind of end up going towards is this notion of distance, right? Like Pranay mentioned. So can anyone tell me if I give you 2 points, x1, oh my God, y1, it's fine, I can do this, no need to text, no need to bring out the text, y2. What is the distance between these 2 points?
It should be y2 minus y1 by x2 minus x1, depending
What
on.
kind of distance is that? So let's talk about
If you want to go for the vertical distance, it's y2 minus y1. If you want to go for the
sure.
horizontal distance, it's x2 minus x1. So,
Is there, okay, sure. Though that is a notion of distance. So that's called the taxi cab or Manhattan distance,
right,
right?
but if you're talking
Because
about like the gradient distance, then
what's a typical distance we use? I think Arjun's kind of mentioned in chat. So what's a typical distance
Mhm.
function you'd use for, let's say, 2 points in 3D space?
I think Arjun has answered the square root of this
Oh yeah,
thing, but
fair,
it's
fair,
not
fair.
entirely correct though.
Yeah, so it's almost there. So it's square
Mhm.
root of, do you guys want to try?
don't you use like Pythagoras theorem then?
Essentially, yes. So what would that be?
So then it would be root of y2 minus y1 square whole square plus x2 minus x1 whole square.
Right. Cool. So
Mhm.
yes, perfect. Correct. So Arushi is also correct. I think Arjun also basically got it minus some issues typing in the chat because it's difficult. And yeah, so this is what the kind of distance we typically use. So what we want is, right, this is giving us a distance between 2 points, right? Now, in our data set, like all these points, that's a data set, right? So that's again another term. So this is a set of data, right? Each point is a data point, and taken together, it's our data set. In our data set, so let's say we fit a particular line of like some mx and some c, right? Um, the distance we end up caring about, so from each point, right, there's an infinite number of distances to this line in some sense. You can take this distance, or you can take this distance, or you can take this distance, right? which one do you think we care about?
The shortest distance, I'd assume.
Perfect. And what is the shortest distance onto this line?
Well, it would just be the what's it, perpendicular one,
Yes,
right?
exactly. So the
Correct.
perpendicular kind of drop from this point to this line, right? And we won't go to the, like, you can do a bit of geometry to kind of figure out how to compute this, but it's not too complex. So we won't like go into the formal kind of idea of it. But you have this. So we want to look for all of these points, right? We look at all of these like perpendicular drop distances. And what we want to do is something called, um, and I know some of you are in 10th grade, some of you might be in like 11th or 12th. Have any of you done linear programming?
No, I haven't heard of that before.
No, okay, no. Okay. No, like if you guys had, I could motivate it in a certain way. But basically, are you guys familiar with the idea of like optimization problems, like minimization or maximization? This might come up in calculus as well. Okay, no.
No, I'm not.
Okay. So the basic idea is, right, you have all these distances, right? They have some formula, right, which is dependent on. So this line here is y is equal to mx plus c, right? For some m and for some c, right? So these distances you will also get will be in terms of m and c. Like those will be the two unknown variables because everything else is known, right? So you know where the point is. All you don't know is the line. And once you work out the geometrical kind of derivation for this perpendicular drop distance, it will basically be a function of m and c. So which m and c you set, and this is obvious to see, right? If I set a different m and c, so if I get a different line, these distances will be, the perpendicular drop distance will be different, correct? Right? Does that make sense?
I'm not. Oh yeah, I guess because you can say that by using like by I don't know actually.
So
It
what
is
I'm
confusing. I don't quite get it, but
what I'm basically saying is like, okay, just consider one point, right? So think about one point like this guy, right? For any two lines, so the point doesn't change, right? The point is going to stay the same for both guys, correct?
yeah.
The point stays the same. Only the line has changed. So this distance, right? The formula you get for calculating this distance and the formula you get for calculating this distance, since the point is kind of a constant here, the only thing changing is the parameters of the line, right? The m and the c for the line.
Yeah, for the
Right.
two different lines.
Right. So for this points a distance, there'll be kind of an expression you'll get, which is expressed just in terms of m and c.
Okay, wait. Are
Makes
we
sense?
is it like using circle theorem or something? I don't quite get it.
You don't have to think about the theorem. You just have to think about the fact that there's some expression we have for distance, right? Similarly,
Yeah.
how we have this distance formula, we'll have some kind of distance formula for this perpendicular drop distance from any point to any line,
Okay.
right?
So it's like it's just a formula for it.
Yeah, and that formula will just be in terms of m and c because the point is a constant in some sense, right? Because we know the
Okay.
point.
Yeah.
Okay. So then the question becomes, we want to do this thing where we want to kind of minimize the average distance over all the points. So you take all the distances to all the points. So take m and c, like an arbitrary m and c, like as variables, right? Take all the distances from all the points, like you'll get some expressions in m and c, so some equations in m and c for that, right? Not equations, just expressions, right? And what then you do is you do a thing called optimization. And again, since you guys haven't done linear programming, optimization is a bit hard to explain. But all optimization is about is if I give you a function, right? Like if I give you the function, but if I just give you some function, let's not worry about a particular function just yet. But if I give you a function, the idea is optimization tries to change some variables that it's allowed to change. So in this case, that would be m and c. So m and c are kind of our decision variables, which we're allowed to change in the optimization. And it's going to try to change them so that it minimizes or maximizes a set of a certain function, right? So we have what we then have is this big average function of all these distances. So each distance is in terms of m and c. We just sum them all up and divide them by the number of points. So that whole thing itself, that average, is also a function of m and c, right? And then all we do is we do this thing called optimization, which says ki I want to find the m and c the slope and the intercept key values, which will minimize the average distance to these points, right? Even if you kind of don't get the jargon here of optimization or of the decision variables or whatever, that might be overloading you guys. But do you basically get the idea of I don't want to minimize distance to one point. I want to kind of minimize the distance to the average distance to all the points, right?
I don't quite get how you finding the average distance in terms of MNC though.
So the distance here will come out for any particular point will come out in terms of MNC.
Yeah,
You agree with that?
yeah.
So what is the average then? It's just the sum of all of those guys divided by the number
Divided
of
by the
points you
number,
have, right?
right? Okay.
So
That makes
then that's just a function of MNC still, right? It's just a sum of a
right.
bunch of
That
functions of
is.
MNC, which is still a function of MNC.
Okay. Yeah, okay. That makes sense then.
So then you can use calculus essentially, and you'll learn more about this in the courses you'll do. So you can kind of learn about how you do this optimization, and you can arrive at a value of MNC that minimizes this average distance, right? And would you guys agree that if we minimize this average distance, that that's a good kind of heuristic, or that's a good kind of um, intuition for what a good, well-fit line is, right?
Because then likely the most of the points are closer, right? As close as possible, because the average distance is least.
Exactly, right? So like this case is a good illustration of that in some sense. So the average distance here is like, I mean, for the distance to every point is basically the same, is the claim. And the average distance minimization will kind of give you this line in between them, right? So if you guys agree with that, then we've basically covered the intuition behind linear regression that we wanted to touch on for this session. So we can kind of go into the part where we discuss the courses themselves. But if you guys have any questions about this or want to ask us about, what's the upshot of this, why do we care, or if you guys have any questions overall about this segment, you guys can go ahead and ask right now.
Oh, I think it makes sense now.
Yeah. So, like I said, before we just move into the next section, I'll just kind of give you guys again the big picture here. The big picture here is that now we have a mechanism that allows us to, based on some features about any kind of object, right? And the object need not be like a physical, real object, right? It can be abstract things like words, or it can be abstract things like. So in the case of okay, I won't jump the gun here, but the basic idea is that it allows us to now take some real numbers, a set of real numbers, right? And based on that set of real numbers, predict another real number, right? That's what linear regression is doing. It's taking a bunch of real numbers, and it's based on some it's learned some statistical pattern, right? That allows you now, based on that data, predict a new real number that is somehow statistically related to the previous set of real numbers, right? So now don't think about something like, houses. Think about something like text, right? So you can represent text as real numbers in certain ways. I won't get into how, but you can do it. Trust me. It's called encodings, right? And once you do that, what you can think about doing is, okay, let's say I have 100 words in my dictionary. That's all I know. I know 100 words. And the simplest encoding is I'm going to represent them as 1 to 100. So the word the is number one. The word a is number two. The word car is number three, and so on, right? So I have 100 such words, right? And I kind of give you a sequence of words. So let's say the sentence is the car is moving. So let's say two is the thing for the, three is the thing for car, five is the thing for is, and seven is the thing for moving, right? Then what I can kind of do is I can try to use a lot of text data that I've seen, right? So what I can do is I can see I've seen a lot of text data, and I've seen in some text I've seen the car is moving quickly, or the car is moving very fast, or the car is moving slowly, right? So I kind of have a bunch of kind of examples of what comes after this word, right? Typically in sentences. I've taken a lot of books. I've taken that as data, and I've seen whenever I see the car is moving, either it can be followed by a full stop with some probability P1 or P full stop, whatever, or it can be followed by a slowly. Oh my God, I'm sorry for the handwriting here. It can be followed by a slowly with some other probability. So you guys can make sense of this, right? You guys have done probability in some
Yeah.
capacity.
Yeah.
So you guys can, well, you have some data which says this many times when I see the car is moving, let's say I've seen this sentence 100 times, the car is moving, or this phrase 100 times, the car is moving, this incomplete sentence. 10 times out of that 100 times, I've seen full stops. So that means full stops have 10% probability of coming after this, right? 15 times I've seen slowly come after this. So 15 by 100 probabilities of, or 15% chance of slowly coming after this, right? So you take all these probabilities, and what you can then do is for each of your 100 words, there'll be some probability associated with it, right? So you have 100 such words because that's our dictionary. What you can do is, based on this, you can train 100 linear regressions, right? Which will then kind of predict, based on any incomplete sentence you give them, they will predict what is the most, what are they predicting? They're predicting the probability of the next word coming, right? So one linear regression model is predicting what's the probability of full stop being the next word. One guy is predicting what's the probability of slowly being the next word, right? So you take all of those guys, see whichever word has the highest probability of appearing next, and put that there, right? And in this construction alone, what you arrived at is a very primitive, a very oversimplified, and a very simplistic. Again, I make no claims about this being like a robust system, but you've arrived at a very simplistic kind of simulation of what something like ChatGPT is doing when it's kind of talking to you, right? I'm guessing you guys have all used ChatGPT now, right?
Yeah.
Yes. Yeah. So this basic mechanism of regression, again, with a lot of kind of bells and whistles on top of it to make sure we can actually do this practically and the output is good, with a lot of kind of bells and whistles on top of it. This same kind of regression mechanism is all that's really informing all of this kind of artificial intelligence and machine learning uh, buzz you're seeing right now, right? This is the basic primitive element that we then take and use in certain ways and augment with other techniques and combine with other kind of again techniques I have to say, but you kind of do this kind of augmentation and combination of different techniques with linear regression to arrive at these kind of big machine learning models, right? And that is kind of the beauty, and like that's the kind of beauty of artificial intelligence, is that it's all kind of based on this very simple idea of fitting the best fit line, right? Or finding the best fit line, which is obviously quite impressive that you can jump from there to there. So yeah, that's all for I think the interactive session. If Gautam has any comments to make here, he can. Just don't like roast my simplified explanation. That's all I ask. Okay, so then yeah.
I think it was a very well put, sort of very oversimplified view, but if anyone has any question, we can take them up, or else we can move to the next section.
I would like to add, like the high schooler in me was uh, completely, curious. And thanks for breaking it down so well. Because the last time I did math was in my high school, and I could make sense of all, like most of it, not the math part of it, but of course, like how to find the best fit line and uh, averaging all out, all of that, and how it can be used, and it is being used to find out patterns um, in big models that we use in different industries currently. That's very helpful. I believe Pranay wanted to say something, and I saw that they unmuted. Pranay, please, you can go
Uh,
ahead.
yeah, I understand the idea of what's happening. I just don't get why we're doing separate linear regressions for each of the different probabilities, because we already have the probability. So I don't see why we have to create a linear regression on it. Since it's a linear line, it's not like it's changing the probability. So
Okay, I get what you're saying. You can learn more about this in the courses themselves, or if you, if you want a rough understanding of why this is, um, basically, again, the probabilities aren't really exact, right? If I take two data sets, if I take one data set, which is like some set of books and some set of like articles I've taken it from, versus if I take another kind of data set, there's no exact real probability. I'm taking like take all the written word, I'm taking a very small subset of that and trying to learn the best statistical, like I'm trying to learn a simplified representation of that and hoping it generalizes to the rest of the world, right? Because what if my kind of data is just really bad, and in the sense of, if it's really bad in the sense of key, it's written by the same writer, right? So the kind of same patterns are going to reoccur over and over, right? And if I try to then apply that to something outside that data set, what's going to happen is it's not going to give me very good results. It's going to kind of end up not being able to emulate, let's say, someone else's style of writing, essentially, right? So what you want to care about doing is you kind of have these different distributions that are coming from different parts of the data set. So, some writer writes in this way, some writer writes in this way, some writer writes in this way, and they're very distinct, right? So what linear regression, just like we kind of did for data, the line isn't exact, right? We're trying to find the best fit line. So our probabilities are also kind of noisy in some sense, these transition probabilities we have, right? And based on our data, we want to kind of find the best actual probabilities. Right now, we just have estimates of those probabilities based on the P1, P2, P3 stuff. But what we want to do is we want to find a kind of more robust estimate of those probabilities, right? But you're right in saying that 100 linear regressions is kind of a bad way to do this, which is why that's not how it's done. But that's the basic primitive that's applied to it, of saying ki I want to predict, like the basic idea that's still applied to it is I want to predict 100 probabilities for 100 words and then find out which is the most likely, right? You actually kind of do it in one step in some sense in modern transformers, like you do it with one matrix multiplication. But you're right in saying that that kind of 100 linear regression system is inefficient. My whole goal here is just to kind of give you the idea of what's happening, right? And the simplest way to do that is through the 100 linear regressions.
Yeah, okay, I get it now. So the idea is basically just that because each subset's giving you different values, you end up with different data, and then you have to find the best fit
You have
between
to
them.
find the closest approximation that
Yeah,
that
okay,
well represents all of them, right?
all right.
Yeah.
Thank you.
Wonderful. Thanks so much, Sanskrit and Gautam, for walking us through, a teaser of how your classes would look like during summer 2025. Really, really excited and awed with the activity itself. Very interesting. Before we proceed, yeah, we have a question. Can we take? We'll take the questions after we have gone through how the courses would look like. I would just quickly share my screen and request Sanjit to go through your course that we are going to offer this summer, and then we'll proceed with Gautam as well.
So yes, so I'm the teaching fellow for the course, which is the Mathematical Foundations of Computer Science. And what this course focuses a lot on is, as it kind of says in the box, the mathematical foundations of computer science. So the course is essentially divided into four distinct, kind of topics as such, which are listed here. So the first one is probability theory. And this is where, Pranay, your kind of question is also answered in some sense about how when we have a big population which we're sampling a subset from, how just taking what we can see in that subset and trying to apply it to the entire large kind of population is always going to result in our destruction in some sense, right? So probability theory is all about understanding that the world around us does not really operate in deterministic ways as far as we can tell. There's a lot of kind of randomness involved. There's a lot of kind of noisy or fuzzy processes involved. And the goal of probability theory is to kind of formalize this fuzziness in the natural world and see how we can kind of deal with it, how we can live, how we can make decisions despite the uncertainty all around us, right? So that's the first part of the course. The second part goes into game theory. So game theory is an interesting one because it's very much it's very much a kind of field at the intersection of computer science, economics, social sciences, and also to some degree math, right? Which we'll see all the applications. They have very nice interpretations of game theory in all of these different disciplines. But the basic idea is a game. You don't want to think of this as necessarily, you can think of it as a game like you might play, but you want to think of it as a simpler process of where, there's kind of a state, right? Like two companies are competing in some sense, right? Let's say. and each of them can take certain actions, and each of those actions have an associated kind of payoff or a cost to them, right? So the question is, how can we model these kind of competitive decision making processes? And when we are in these adversarial situations, right, where we have kind of enemies, or where we have kind of, there's this concept of games where you have full information like chess, or games where some of the information is obscured like poker, where you don't know your opponent's hand, right? So the question is that in these different types of games, what are the kind of basic principles we can hold on to which work everywhere? And this again ties into the question of how do we make decisions under external pressures or external threats or uncertainty, right? So game theory is all about kind of modeling games and seeing how we can solve them, right? And that solving is how decisions are made in some sense. Then we go into some more core CS or core kind of standard CS stuff, which is algorithmic thinking, right? So you guys know what an algorithm is, I'm guessing.
Yeah, an algorithm is just like any process that it's just a process really.
It's a
You usually don't.
well-defined kind of process. That's a perfectly
Yeah.
fine way of understanding it. So algorithmic thinking is, it's more than just, so I've kind of talked about how you design algorithms to solve important problems and measuring their success, but you can also kind of think about how you can look at the world around you, right? And you can look at a system that exists in the world, and you can start to kind of reverse engineer the processes by which it arrived at its current state. Because, like you said, algorithms are processes in a sense. And, kind of, if you have heard the term systems thinking or kind of design thinking to some extent, that whole process of breaking down a big system you see in the world into its constituent parts and understanding how each point or each part kind of contributes to the entire system is the basis of algorithmic thinking in the real world. So the course is kind of going to cover obviously the foundations of algorithm design, which is like the more kind of theoretical work, and then also kind of move into, what can you do with this knowledge you have of analyzing the success of algorithms to kind of maybe analyze how the emergence of certain systems in the real world, right? And finally, there's a component on artificial intelligence, which is all about how we can embed our biases or our heuristics. By R, I kind of say statistical biases or statistical heuristics, not human biases or human heuristics, hopefully, but statistical biases or statistical heuristics, right? So what we did there with the house prices is we looked at our data. Our data has a story to tell, right? Our data has some biases. It's saying that houses with more square footage typically have a higher price, right? But not always. So it has some biases. It's kind of providing us, right? So the whole idea of artificial intelligence is to allow machines to reason about the world with heuristics as opposed to kind of deterministic means, which is typically how algorithms work, right? You give the same input, you will mostly get the same output. However, artificial intelligence is all about talking about how, you know, the world around might not be as simple as we can model it like in a deterministic way, right? There's a lot of noise in our kind of data we've collected, and there's a lot of noise in how we dealt with the data. And the kind of subset of it we've selected has certain biases. So how can we embed those biases or heuristics into our machines and allow them to kind of make predictions about the world in a noisy way in some sense, right? And all of this, so these are the kind of theoretical components and the learning outcomes or the kind of topics we'll go over. But besides that, all of this will be underpinned or held together by hands-on projects which you guys will be taking up for each of these modules, which will tie in what you're learning with some practical essentially, not like practical experience of working with code, working with these theories, and actually constructing programs out of them. So the by the end of the course, what the hope is, what the kind of final project is that you'll be constructing a bot that can play poker, and then we'll have kind of a versus battle of all the bots and see who's kind of constructed the most robust or the most kind of um correct or the most kind of strategic poker bot, right? And that's what the course is kind of going to look like. And yeah, it'd be great to have you guys there.
Sounds pretty fun and interesting. How long is the course? Like when does it start and how long?
Um, Yeah, I think yeah.
The course starts on 17th of May, and they would end by 14th of June. Most of you would have classes over the weekends, which is Saturday and Sunday, for 2 hours each, at 11 a.m. to 1 p.m. And on Saturdays you would have sessions with the faculty, and on Sundays you would have sessions with your teaching fellows in your meeting currently. Our applications essentially close on 6th of April, and we would come to that, of course. Before doing that, thanks, Sanjutta, for walking us through the learning outcomes for your course and how does your course look like. I would request Gautam to proceed ahead and share with us about the course that you would be offering.
So hi, I'm the teaching fellow for the Applied Data Science with ML and AI course. And in this course, we'll be focusing a little bit more on the applied side of the data science. So to put put it into perspective, the data science is more about, as the also told, the storytelling, starting from the data towards getting your insights or getting your results. So the module will be, or the course will be divided into roughly 4 modules, uh, where we first start with the understanding the data and different type of data types and what are the different set of operations that we can do on different type of data, and how do we understand these different data types, and what are the strategies we can follow to sort of process and get insights from this different type of data. And the second will actually focus more on the in-depth understanding, or for example, given a particular type of tabular data which involves all numbers and different measurements, what are the different uh, approaches we can do, or what are the different exploration we can do on top of the data, and can we uncover some sort of patterns, or can we uh, get to know those biases itself. So the one example that we saw in previous example, in the previous exercise where we were working with house prices, so when we plotted those house prices over that graph, we saw that intuitively with increase in house area, there's an increase in house price. So uncovering those sort of patterns will be the main focus. Uh, and this will be done through different statistical tools and different methods that we'll learn throughout the regular sessions. And we'll apply these tools or these methods, these algorithms in the second class, which is the hands-on approach. And then we'll also move towards the visualization or the storytelling part of the data science, where we sort of take all the patterns that we have discovered and all these information, and then visualize them, or uh, put them into a presentation through write plots, write graphs, and make sure that all of the data that we processed and all of the results that we are getting actually make sense. So can we interpret those results, or can we explain those results through some visualization methods? And then towards the end, we'll also cover basic uh, up some basic ML and AI, where we, as we covered today in linear regression, we'll look at some more models, some more ways to model the data, and what are the different kind of models, or what are the different kind of approaches we take to sort of take or model different kind of data through an overall approach. And we'll also learn all of these in a more theoretical manner uh, in the lectures which will be taken by the professor, and the next day we'll do a hands-on approach of everything that we learn. So the project idea for this course will have sort of two components. So one is where we'll ask you to collect your own data on a particular topic and then perform these analysis on top of it. So to give you an example, in last year's course, student uh, took various kind of data which was associated with the food that they ate during this 1 month period every day. And towards the end, we built some models to get some insights on how how nutrition was playing a part in their daily life. And the second part also includes where I'll give you some data set and then ask you to apply different methods and see uh, what unique insights you can come up with. And then combining these two projects, these two short projects, will be able to understand the entire journey from taking the raw data and then pre-processing it, exploring it, visualizing it, building a model on top of it, and then presenting your overall results.
Great. Thanks, Gautam. Thanks for sharing the learning outcomes and, brief summary about what your course is about, what you will be going to do during the summer in your course with data science, ML and AI. Proceeding further, we have posted the links to both the courses. We have also shared the course catalog with you, in which we also have like our third course we are offering around computer sciences, which is AI for tomorrow's world. Um, Moving forward, I would just cover certain details about the Horizons Achievers program. So this time we are offering around 15 courses across different disciplines. We prefer small cohorts and immersive experience during the classes. This time, students would not only have an opportunity of doing the course, but they have extended opportunities of receiving mentorship as well as an internship with the teaching fellows and the faculty. But it depends on how you perform throughout the course as well. Um, you would also be working on a capstone project, as Gautam and Sanskript have also mentioned in their respective detail while describing about the details of their respective courses. So you would over the 4 to 5 weekends, you would be working over a capstone project, and by the end of your 5 weekends, you would have a project would be that would be very original and done by you. In addition to that, if you perform excellently throughout, you may also receive a letter of academic appreciation, which would of course be an add-on to your profiles that you may be working on. Over the last year, we have seen that the experiences of our students have been great. Most of the students who do join the course, they end up completing the course. So we have a 95% completion rate. In addition, most of the students have rated highly our Horizons Achievers courses. Um, yeah, I think we have covered more or less everything. And I saw that somebody had posted questions over the chat box. This is the right time. You can ask questions about Horizons regarding dates, regarding the courses that we just covered. Please feel free to unmute yourself, ask the questions, or drop in the chat box. And I would just reiterate the dates for the program are 17th of May to 14th of June. And our application deadline is 6th April. So would urge everyone who is keen to join to apply as early as possible, because we do prefer small cohorts. Once our seats are filled, we would just close the applications. Arjun had asked the question, can you recommend some books or courses to understand this better? So if Gautam, Santrap, if you have any insights on that and can recommend something for high schoolers, that will be great.
So I think, or I'm guessing this was in reference to the linear regression and the machine learning kind of bits. So in reference to that, I think the kind of definitive reference most people use nowadays are these things called the Andrew Young notes. So it's a professor I'm not sure where actually Gotham might know this. Stanford, maybe?
Stanford.
Okay, Stanford. So Andrew Young so I'm putting in chat. Andrew Young's notes on machine learning. So this is one of the more popular kind of resources. It does assume a bit of mathematical background, so do expect that if you want to work through it, you will have to work through it. As in, you will have to kind of maybe also seek out some other resources on like some calculus, some linear algebra. But I think it is generally a pretty well written book. Another one I'd recommend is this one called one second, let me see, Learning from Data by Yasser Abu Mustafa. So wait, I'll put this. There's also quite a nice book, and I think there's an online course alongside it also that you can find. So it's here. And this one is also I find this one to be more of a it's more of a book. So Andrew Yang notes are kind of lecture notes in some sense. Like those are the kind of notes he uses for his own lecturing at Stanford. Whereas this Learning from Data book by Mustafa is more of a book, right? It's a textbook. So it kind of dives more deeply into the kind of intuitions behind things, is more, it has more prose in some sense. So there's more text which explains things and gives intuitive understanding of like ideas. And I think it's a pretty solid intro as well. So these are the two kind of books I'd recommend. If Gautam has something from his side, he can, you know.
No, I think these are pretty good resources. I also personally used uh, Professor Entry's notes as well when I was studying ML. But it, other than that, you can, if you want to have some uh, more mathematical intuition for these methods, you can also refer to the Mathematics for Machine Learning textbook. I'll just uh, send it link. Yeah. So you can also look into this textbook if you are more mathematically inclined towards learning how these methods came up or what's the intuition behind this. But I think these two or three resources uh, can help you a lot if you are learning more towards linear regression and building up your foundations on this topic.
Yeah. So
That's helpful. Thank you, Gautam. Thanks, Santripta. If any one of you have any questions regarding the course, regarding the program, please feel free to ask. Great. I What we would also do is I'm dropping in the link to the application form in case any of you want to go. You can just directly go and enroll yourself as well. Read up about the course using the course catalog. I believe that should be helpful. Great. Thank you, Arjun. Thanks, Neetu and Pranay for being with us. Um, Thank you so much, Gautam and Santripta, for walking us through your courses, for doing this immersive activity, which is very insightful and helpful to understand how your classes would look like during summer. We're very excited. Looking forward to you, both of you teaching during the summer with us. Thanks, Arushi and Aditi. They are from Office of High School Programs. They have also been here with us. Thank you everyone for joining the session, and we would share the webinar recording as well as the links that we have posted um, after the session. Thank you so much.
Thank you.
Thank
thank
you.
you
Bye,
guys.
everyone.
Thank you. Bye.